है।
पढ़ाओ। चलिए लाइव जा रहा है अब स्क्रीन पे, टॉप कंप्यूटर स्क्रीन से ऊपर जा रहा है।
शेयर स्क्रीन करना पड़ेगा। Should I start? Should I start? I cannot hear anyone. Hello? Hello? हाँ जी बस।
वो ऑफलाइन है नहीं, कुछ वो म्यूट।
हाँ डॉक्टर राहुल प्लीज अनम्यूट योरसेल्फ। तो दूसरा भी तो कोई है ना, सेकंड पर्सन है ना,
दो थे बट
अजीत है ना.
हाँ जी बोलिए.
आवाज
Okay, okay. So you can hear me?
I can hear you.
Okay, fine. So we can also hear you.
लेकिन मुझे कुछ भी नहीं दिख रहा.
If you want to give your presentation, you can share your slide.
Can you hear me?
Yeah, we can hear you. You please share your slides.
कि स्क्रीन पे तो कुछ भी नहीं दिख रहा मुझे. मेरी स्क्रीन पे तो ब्लैंक है. आपके कॉन्फ्रेंस में कुछ भी नहीं दिख रहा मुझे इस पे.
कैमरा ऑन कर, एक बार देख लीजिए, कैमरा को ऑन ऑफ कर लीजिए सर.
कॉन्फ्रेंस का
एक बार नीचे कैमरा बटन होगा, स्टॉप कैमरा, उसको फिर स्टार्ट कैमरा कर दीजिएगा.
नहीं, लेकिन आपका मुझे कुछ नहीं दिख रहा उधर से. कॉन्फ्रेंस का कोई ऑडियंस कोई इस तरह कुछ नहीं दिख रहा मुझे उधर से.
सर आपको यहाँ पे जो ऑडियंस है वो आपको सुन रही है, तो आप इस बड़े स्क्रीन पे हैं, तो आप अपना कैमरा ऑन
आपको हम सुन पा रहे हैं, सिर्फ हम आपको देखना चाहते हैं, तो आप अपनी स्लाइड शेयर कीजिए.
Can you hear me? Can you hear me? Can you hear me? Can you hear me? Hello? Can you hear me?
Sir, you are audible. You can start your presentation, sir.
Okay. Just one second.
आप स्लाइड व्यू में जाइए, स्लाइड शो में जाइए.
दिख रहा है सही?
गो टू स्लाइड शो.
स्लाइड शो में.
हाँ.
Can you see?
Yeah, we can see you.
Or slides? Can you see the slides?
Yeah, we can see the slides also.
Okay, ठीक. Okay, thanks Dr. Kavita to invite me for the talk. So my topic of the talk is recent developments in materials for supercapacitor applications. So I'm from Connecticut. If you go from New York to Boston, so we are 90 miles north of New York. So here is Hartford, and near the Hartford we have Hartford, the capital of Connecticut, and we have Central Connecticut State University. So our university is here, and this is the campus map of my university. So this is library, and the library, near the library we have Academic Innovation Hub, which is engineering building. So between library and innovation hub, we have physics building here. So let me skip some slides because of the time constraints. So outline of my talk is motivation, brief introduction of supercapacitor, effect of multiple carbon nanotubes on electrochemical performance of MnO2, effect of RGO on electrochemical performance of super copper sulfide nanostructure for supercapacitor, binder effects, and the effect of biochar. So let me. Okay. So now we are looking for the alternate energy sources, and we have the challenges with the alternative sources. So the most challenges is how to store the energy. Okay. So most of the alternate energy sources are in the research phase. So power production for these sources are large scale is still challenging, while hydroelectric power generation being exception. So how to store the energy produced by the alternative energy sources? So to overcome the solution for the energy storage, we are looking for energy storage devices such as rechargeable batteries and supercapacitors. So supercapacitors are the high energy storage device with higher power density and high energy density than conventional capacitors. So the advantage of the supercapacitors are high power density, possibility of fast recharge, large cycling capability, and excellent reversibility and longer lifetime. So we have two types of supercapacitors: electrochemical double layer capacitor (EDLC), and then first present by General Electric using activated charcoal as a plate. The charge stored take place electrostatically or non-Faradic. That is, no shifting of the charge take place between the electrodes and electrolyte. So the good electrical conductivity, excellent mechanical stability, high reversibility, along with high cycle stability. So the disadvantage of the supercapacitor, or you can say challenge, is low specific capacitance. So EDLC mainly employed by carbon electrodes materials, graphene, activated carbon, nanostructure carbon, and the carbon aerogel. So we are the pseudocapacitor or the redox capacitors. So energy stored in the pseudocapacitor via fast and reversible Faraday redox process limited to electrode-electrolyte interface. So we have used the transition metal oxide like iridium oxide, ruthenium oxide, iron oxide, manganese oxide, or transition metal sulfides, conducting polymers like polyethylene polypyrrole for the pseudocapacitors. So they have the relatively high specific capacitance and superior specific energy. The major drawback is low conductivity. So as you saw that in the EDLC, we have the low capacitance and here we have the low conductivity. So we can make the hybrid capacitors using the properties of the both pseudo capacitor and the EDLC. So we can combine the transition metal oxide or sulfide or polymers with the carbon material, and it works for the hybrid capacitor. So we can see that from the previous work, Hot et al. Represent that if we add 7% of reduced graphene oxide in copper sulfide, so the capacity increases up to 235 ampere per gram. So the like farad per gram at 1 ampere per gram. So in this picture, we can see this is the copper sulfide with 7% RGO, and we got here. So this is the without with like 7% RGO here, and this is copper sulfide, pure copper sulfide here. So you can see by adding the 7% RGO, the capacitance increases too much. So we are using this approach of the hybrid supercapacitor. So we want to see the effect of multi-wall carbon nanotubes on electrochemical performance of MnO2 for supercapacitor applications. So we are using the manganese oxide because it is natural abundance, low environmental we have less toxicity and cost effective. And the carbon metal serves as a highly conductive and stable current collector. So its interconnection holes are beneficial for the ion diffusion. Okay. The improvement of the active materials mainly involve high reversible capacitance, structure stability, and rapid cation diffusion at high charge discharge rates. In the synthesis process, we synthesize MnO2 by dissolving the appropriate amount of potassium permanganate in 3:1 volume ratio solution of DI water and the ethanol, and we stir for 1 hour. And then precipitate was washed with DI water, ethanol solution, and dried in oven for 80 degrees Celsius for 24 hours. To synthesize the MnO2 multi-wall carbon nanotube composite, we suspended the carbon nanotube in a like 1 milligram, 4 milligram, and 10 milligram per ml carbon nanotube in 3:1 DI water ethanol solution, and then we did ultrasonication for 30 minutes. So when the multi-carbon nanotube is suspended in the solution, then we add the potassium permanganate in the solution and stir for 1 hour. And after that, we just centrifuge the precipitate and then wash and recover. So X-ray diffraction of the material shows the diffraction peak at 37.74 degree, so which belong to 131 plane, and 66.26 is 003 plane, and these peaks can be indexed to tetragonal alpha MnO2. So these peaks are remaining in the composite structure as well, as you can see here. So this is pure MnO2, and then we got this is the composite structure. So all peaks are in the composite structure. So and then D spacing was calculated to 0.342 nanometer. So that is for the 002 plane for multi-wall carbon nanotube. Then we did a transmission electron microscopy, and we found that so this is a pure MnO2. So we have so we can see that with the 1 milligram per ml carbon nanotube, so carbon nanotube is covered by the MnO2 here. So this is the uniform coating here. When we increase the quantity of the carbon nanotube, So we have less coverage of carbon nanotube, and we have the 10 milligram per ml. So the carbon nanotube here is, so this is very minimal coverage of the carbon nanotube with the MnO2. So cyclic voltammogram study was taken between the minus 0.2 to 0.8 volt. So at various scan rate between 10 millivolt per second to 300 millivolt per second. So all the cyclic voltammogram shows the capacitive behavior of the material. So we can see here, so we compare the cyclic voltammogram at a scan rate of 20 millivolt per second, and we can see that at 20 millivolt per second, the MnO2 shows 62 farad per gram specific capacitance, and the carbon nanotube 100 milligram 191, 400 is 222, and 1000 is 188 farad per gram. So we can see that specific capacitance like decreases when scan rate increases here. So this log of current and log of scan rate graph shows that the slope. So if the slope is 0.5 is pseudo capacitor and 1 is EDLC. So we can see that in our all the materials we have the slope of cathodic slope is 0.42, 0.61, 0.54, 0.47. So it indicates that all the materials is like pseudo capacitive. So galvanoelectric discharge studies was taken at different current density at 0.5 ampere per gram, 1 ampere per gram, and 2 ampere per gram. So in a 3 electrode system. So you can see that at the different current densities, MnO2 shows at 0.5 ampere per gram, MnO2 shows 124 farad per gram, and the MnO2 CNT shows 145. At 400 we got 135, and 1000 is 102. So as we saw that in the TM picture, that with 100 milligram carbon nanotube we have the better coverage of the carbon nanotube with MnO2. So we have the smooth surface. So or we increase the surface area. So that's why it is responsible for the higher specific capacitance with carbon nanotube of 100 milligram. So as we increase the carbon nanotube, specific capacitance decreases, so which indicate that the low carbon nanotube is favorable for the increasing in the capacitance. So further we did the effect, we studied the effect of the reduced graphene oxide on electrochemical performance of copper sulfide nanostructure for supercapacitance application. So we use copper sulfide because it is low cost, abundant in nature, and environmental friendly. So to synthesize the copper sulfide, we add the copper acetate in water butanol solution, and then after the stirring we add thiourea, and then we did stirring for 1 hour, and then after that we transfer the solution in the Teflon autoclave. And then after Teflon autoclave was heated at 180 degrees Celsius for 24 hours, and after that it was cooled to room temperature. Material was recovered and dried. So XRD indicate the covalent copper sulfide hexagonal structure. So with corresponding planes of 002, 100, 101. So like all these planes are corresponding to covalent copper sulfide hexagonal structure. And crystalline size were calculated as 35 nanometer and 32.9 nanometer for copper sulfide and copper sulfide RGO. So pictures show the scanning electron microscope, and it shows that in the copper sulfide here, so we have the hexagonal structure, hexagonal copper sulfide structure here. All we can see here, and this, so all the material like agglomerated here. And when we add the reduced graphene oxide, so copper sulfide got like embedded between the plaques of the, or you can say plaques of the copper, of the reduced graphene oxide. So surface become more smoother, and it increase the surface area. So we can see from the cyclic voltammogram that all the materials have the capacitive behavior, and copper sulfide nanomaterial showed a specific capacitance of 207 farad per gram. So while copper sulfide RGO shows 350 farad per gram at a scan rate of 1 millivolt per second. So similarly, log of current and log of scan rate graph shows the cathodic anodic like slope as like B value is 0.563, 0.583 for the anodic and cathodic peak, and for the reduced graphene oxide it shows 0.48 and 0.51 respectively. So which indicate that the material has the pseudo capacitive behavior. So galvanostatic charge discharge studies confirm the supercapacitor behavior of the electrodes, and we can see that at 0.5 ampere per gram current density, copper sulfide shows 207 farad per gram, while copper sulfide RJ shows 350 farad per gram specific capacitance. So we can see clearly here at all current density, the copper sulfide RJ shows the improved capacitance. Okay. So now we did the binder effect of MnO2 because binder plays an important role in the supercapacitors. When we make we make the electrode, we mix our active material, like in this case MnO2 CuS RgO. So with 10% binder. So generally we use 10% binder, but binder like covered the surface of the material, so it decrease the capacity as well. Okay. So now we want to show the effect of binder on the supercapacitor performance. So for that, for the synthesis of MnO2 CuS RgO composite, so we use copper sulfide as we synthesized earlier. So now we get the RgO in the water ethanol solution, and then we add the potassium permanganate, and in the solution we stir for 1 hour, and after that we add the copper sulfide. So we add copper sulfide in this, and we get the solution here. Just give me 1 second. So I heard that slides are not changing.
You have 1 minute now.
Pardon?
You have 1 minute now.
But slides are not changing. Okay. So let me conclude this.
Yes, please. Thank you.
Okay. So the conclusion of my talk is we can see that the specific capacitance of MnO2 CuS increases by the addition of the carbon material, and then we have to optimize the carbon material concentration in our electrodes. Okay, that's it. So the financial support received from the CUS APU faculty research grant is highly acknowledged, and thank you. Questions?
Okay, thank you, Dr. Rahul, for a nice talk. So since we have a restriction of time, so I cannot accept any question right now. I think later on, those who have questions, they will communicate with you.
Thank you.
Very much.
Thank you.
तो काट देना कविता लॉग ऑफ कर दो Okay, so let us move for the next speaker. Our next speaker is Dr. Praveen Singh. He is a distinguished professor of biophysics at the Indian Veterinary Research Institute (IVRI), specializing in molecular and structural biology with a strong focus on veterinary applications. His extensive research integrates biophysics with animal health, exploring the molecular interaction and biophysical properties of biomolecules to improve the veterinary diagnostics and therapeutics. His contribution have positioned him as a leader in the field, particularly in the application of cutting-edge biophysical technologies to the veterinary science. So, without wasting any time, welcome Dr. Singh.
Thank you, ma'am. प्रेजेंटेशन में लोड किया हुआ था
हाँ
देखो जो सेशन हैंडल कर रहे बच्चे उन्हें याद करने का ही मन नहीं कर रहा मतलब क्या एक ड्यूटी दे रखी है जरा देखें स्टॉक लोड किया है तो
डेस्कटॉप पे
ये ना प्रवीण अच्छा मिल गया
बस ठीक है हाँ इसको फोल्ड
बच्चे बुला लो जो बाहर बैठे हैं ऐसे ही ना उनको बोलो आओ अटेंड करो तो बच्चे तो हमें यहाँ चाहिए चलिए
Okay, I take the opportunity to thank the organizer for giving me the opportunity to present my work here. I will go quickly. So, It's the work that we have done over the years at our biophysics laboratory in the division of biochemistry at the IVRI, and we are dealing with the several types of the sensors, and that are particularly the surface plasmon resonance and the electrochemical sensors and the LFA devices. So all those things together, and we will go slowly one by one. So the biosensing, it is important, and for that to have a monitoring, to have a detection of the disease, and we will discuss about the technological base and certain advantages and why it is so important. We will deal with the electrochemical surface plasmons. So these are the general view that we see. We know the glucometers, we know this is the palm sense, so electrochemical sensors, and it has a electrode in it. So particularly the surface plasmon resonance sensors, and we have a mode of detection, the direct inhibitions, competitive indirect displacement is unique, not available to the ELISA, and rest of the things, and which is very important molecular interaction platform, and its stability is superior. And we know very well the homemade diagnostic, which is like a usually used for the detection of the pregnancy, whether it is positive or negative. So for the similar, and we have done for the several animal diseases at the IVRI. And some of the tests that you know in the market available, that the SARS-CoV test was also available, and the malaria, the brucella, the canine parvovirus for the animal. These are some of the projects that we have carried out at the different level and for the biosensors. And the one scheme, the cast Achilles, where we have a brucella sensor of a multi-crore rupees. And the recent one out of what the work we have done so far on the sensors and the molecular platform, molecular interaction, proteomics, that led to the new project that listed at the number 8, the DBT project on magneto-acoustic electrophorese-based microfluidics for the bovine sex semen sorting. Currently, all the technologies that are available is of the foreign made, and the DBT has sanctioned 645 lakhs. And where the partners are the IIT Delhi, Madras, and Institute of Nanoscience and Technology in IVRI. This is general specific. We need the biosensors, not unknown to everybody is known this. This is the basic fabrication that we did over the self-assembled monolayers over the surface plasmon resonance sensors. We have a gold film, and which we clean it and put some thiols over it, and then attach and through the linkers of a interacting platform, interacting molecules. And this is the basic mechanism